Welcome. I'm Professor Nathanson. This is Math 323. Course listed also as Math 755. And it is a course in ordinary differential equations. So everyone who's taking this course has certainly had at a minimum 2 or 3 semesters of calculus. And the one thing you definitely have to know is calculus, especially techniques of integration. So that's covered extensively in Math 176 or in Calc 2 in most schools. And so you do need to be able to integrate. You need to know calculus. And this is, of course, in ordinary differential equations. I'm using a textbook which is available free on the internet. I downloaded it and posted it on the website. And the book is this book by William Trench, Elementary Differential Equations with Boundary Value Problems. And since we're fortunate enough that everyone has it, it's completely free, you don't have to buy it, I'm going to follow it very closely. And in particular, what I'm often going to do is just go through each section that we're covering page by page, explaining what we're doing. And that will be the lecture that will often be pre-recorded and uploaded to YouTube. And in our regular classroom sessions, which are Monday and Wednesday at 9 o'clock, I'll review the material again and answer questions you might have about the material, the theory, how to solve problems, and so forth. This is a hybrid class. All the lectures and problem sessions are on Zoom, but all of the exams will be held in person on campus at the regularly scheduled class time. So it's expected if you're taking this course that you are free Mondays and Wednesdays at 9 o'clock, and there's no problem showing up for the our exams or the midterms. We'll have 2 or 3 midterms, as well as the final exam in May. There's no excuse that you have a job at this time, because otherwise you couldn't be taking the class. Okay, so the first lesson is really to cover chapter 1, which is an introductory chapter. And let me turn to that right away. So here we are, chapter 1. So this is really an introduction. It's very simple, but it teaches you the basic terminology we use in the study of differential equations. So let's look at some examples. Some of these are examples that you've already seen in calculus. For example, population growth. I should say, what is a differential equation? There's a simple equation you see in elementary algebra, like x plus 2 equals 5, find x. X is equal to 3. And there the unknown is a number x, and you have to find it. In differential equations, the unknown is not a number, it's a function. And you have to find a function that satisfies some equation. And what makes it a differential equation is that the equation involves the derivative of the function. I know you're supposed to have taken vector calculus as a prerequisite for this, but even if you haven't, it doesn't matter, because in ordinary differential equations, we study just functions of one real variable. So it's just the unknown function is always a function of one variable. And that's what makes a differential equation what is called ordinary. If you're dealing with functions of several variables, you have what's called a partial differential equation. And we don't study them in this class. That's a more advanced class that we offer. So here is a typical differential equation. So y prime is our notation. Y is the function. Y prime is the derivative of y. Sometimes the variable for the function is x. Sometimes it's t. If we think of some function changing as a function of time, we tend to use t as the variable. but it doesn't matter what variable we use, x or t or any other letter. But x and t are really the only ones we're going to see in this class. So typically, if you have a population of something that's growing, it could be people on the planet Earth, bacteria in a petri dish, your money, earning interest in a bank account. We want to be able to say something about how large that population is at a given time. So we're looking at a function, we're using now capital P for the population at time t. And very often, what we know is something about the rate of change of the population. Like P prime, that's the derivative, dp dt, is maybe proportional alpha of P or A of P times the population. So in the simplest case, which you certainly studied in Calc 1, you have a function P whose derivative is some constant times P. So the rate of change, the rate of growth of the population is always proportional to the size of the population. The bigger the population, the faster it grows. The smaller the population, the smaller it grows. So this is really the world's simplest ordinary differential equation. P prime is some scalar, some number, times P. And you learn in calculus that the solution of that equation is P is equal to some constant C times e to the AT. The A, let me just go back. The A is the parameter in this differential equation. P prime is A times P. And in the solution, every solution is of the form some constant C, some scalar, some number C, times e to the AT. So there are infinitely many solutions because you have infinitely many choices for the number C. This number C is sometimes called a parameter. That's just another name for a number. So we would say that this growth equation, this differential equation for the growth of a population, the solutions are a one parameter family. There are infinitely many solutions, and they just depend on some parameter or some number C. If A is positive, you know that e to the AT goes to infinity if C is positive. If A is negative, e to the AT decays to 0. Right? That's what the solutions of this differential equation look like. Now, if we were looking at population growth, let's see population on the planet Earth. If we really satisfied, if it satisfied some differential equation where the rate of growth was directly proportional to the population, this would be the solution. C would be some initial population when you're starting to measure the size of the population. A is positive. The population goes to infinity. Now, we know that's not realistic. When the population is small, it might really grow exponentially. This is exponential growth. It might grow exponentially. But after a while, there's not enough space on the planet to fit all the people. So you can't have exponential growth continuously. And you need, if you want a more realistic model of population growth, you have a model that looks something like this. The rate of change of the population is proportional, A, times the population. But then there's another factor, 1 minus AP. So the larger P is, the smaller this is. So you have, it's not just growth proportional to the population, but there's a kind of a damping factor. Okay? This reduces the size of this A. So when this number is very close to 1, which means alpha P is close to 0, or 1 over alpha is very small compared to P, this is approximately P prime equals A times P. And you should have learned in Math 176, Calc 2 at Lehman, actually how to solve this differential equation. This is what the solution looks like. It looks somewhat complicated, but in any case, we'll learn later on in the course, actually in a week or two, how to solve this differential equation and get this solution. And this is typically what the solutions look like. So if you're looking at population growth, bacteria in a petri dish, animals on an isolated island, in the beginning you have exponential growth, but then as you approach, as the number gets larger, the rate of growth decays, and you actually approach some finite number. So there's actually a limit to how many individuals the environment can sustain. And this is really what you see when you do population studies for example, on islands where there's a finite amount of space and you can count what goes on with competing species. So when the species is small and there's not much competition among members of the same species, it grows, but then the growth slows down and you approach some limiting value. This equation, this differential equation, is called the logistic equation, this guy. And it's a fundamental equation in math and science, economics, medicine, comes up everywhere. Okay. Another example of a differential equation, which I know again one teaches in Math 176 and Calc 2 at Lehman, is Newton's law of cooling. So suppose you take an ice cube and you put it in a room. The temperature of the room is, let's say, 70 degrees. The ice cube is colder. The ice cube is going to melt. Or if you take some boiling water, take a cup of boiling water, you put it in the room, and the temperature of the water is greater than the temperature of the room, the water will cool. And the rate at which cooling, so you're measuring the temperature of the water, the temperature is changing as a function of time. So capital T is the temperature. It's changing as a function of time. So if T is for example, the temperature of the body of the water, and T sub M, this is the medium that you're sitting in, like the room temperature. You look at the difference between what you're measuring and the median temperature, the temperature in the room, and the rate of change is proportional to that. If there's a big temperature difference, the temperature drops or increases rapidly. As the temperature differences get smaller, the rate of change of temperature decreases. That's Newton's law of cooling. This is how, for example, if you watch Law and Order, they start usually with someone finding a dead body, and the coroner comes in, or the medical examiner, and the detective asks, how long has this person been dead? When was this person killed? And the person gives them an answer. And one way you get an answer is from Newton's law of cooling. If you assume that the person had a body temperature of 98.6 degrees, roughly, when alive, and the room temperature is, let's say, 70 degrees, the body is going to cool off. And it's going to cool off according to Newton's law of cooling. So by measuring the body temperature and measuring the room temperature, you can figure out how long the person's been dead. Right? The person's been dead for a long, long time. The body is at room temperature. If the person just died, the temperature is close to 98.6. That's Newton's law of cooling. And there are infinitely many examples of applications of differential equations. This one has to do with glucose absorption by the body. You have glucose in your bloodstream, and as the blood circulates, some of the glucose in the bloodstream is absorbed by the body and used to support all the bodily functions. And there's a differential equation that describes the rate at which glucose is absorbed by the body. The most famous examples are probably from physics, from Newton's second law of motion, which says that when you apply a force to a body, and if you look at the position of the body, the acceleration, the change in acceleration, the acceleration of the body depends on the force. And this involves a second derivative. So you end up looking at second order differential equations or equations that involve your unknown function y, first derivative and a second derivative. This is the sort of thing you'll find a lot in physics. Okay, well, we will have examples in the homework problems all through the semester of applications of differential equations. Section 1.2 has to do with basic concepts. This just repeats what I said a moment ago. A differential equation is an equation that involves derivatives of a function. The order of the differential equation is the order of the highest derivative that it contains. So, for example, population growth involved only a first derivative. So that would be a first order differential equation. Newton's law of motion involves acceleration. That's a second derivative. So Newton's law is a second order differential equation. If an equation involves just one variable, you have what is called an ordinary differential equation. And if your equation involves two or more variables, it's called a partial differential equation. And again, we're only going to study first order equations. Sorry, we're only going to study ordinary differential equations. And in the beginning, we're just going to study first order equations. So the simplest first order equation is an equation where you can write just the first derivative dy dx is some function of x. That actually is too simple, because this just means find an antiderivative of f of x, and this is what integration is all about. You learn to do this in calculus. Y is just the integral of f of x. That's all it is. So this differential equation is almost too simple to discuss. In any case, you spend a whole semester in Calc 2 studying this, which is the problem of integration. So if, for example, you have y prime is x cubed, this means find a function y whose derivative is x cubed, and the integral is the indefinite integral. The answer is the indefinite integral, which is x to the fourth over 4 plus any constant. Right. In general, an nth order differential equation involves the nth derivative of some unknown function y. And in the cases we consider, you'll always be able to write the nth derivative as some function of x, y, and the first n minus 1 derivatives. So here we have some examples. This is first order. This is a second derivative, so a second order. Here we have a third derivative, so this is third order. And here we have an nth derivative, so this is nth order. And again, they're not written strictly in this form, but you can rearrange all of them so they are in that form. You have the highest derivative equals some function of everything else. And so these 5 equations are rewritten here. Okay. And what we learn in this class is how to solve a differential equation. Find the function that satisfies the equation. So there are 2 fundamental terms to introduce. So a solution of a differential equation is a function that satisfies the differential equation on some open interval. An open interval from A to B means all the numbers strictly between A and B. You don't include the endpoints. So a function that satisfies the differential equation on some open interval is a solution. And there can be multiple solutions. There can be different open intervals where you have different functions that satisfy the equation. If you have a solution of a differential equation and you graph it, you get what is called a solution curve. And an integral curve is slightly more general. It's some curve in the plane, and every function whose graph is some segment of that curve is a solution of the differential equation. So every solution is an integral curve, but an integral curve doesn't have to be a solution curve. We'll see examples of that to make this clearer. Right. So here are things, and again, you should know by the time you reach 300 level math classes that when you read a math book or study, you need to have pencil and paper at hand just to work out the details of statements that are made. So here we have the equation x squared plus y squared equals a squared. That's the equation of a circle around the origin, center at the origin of radius a. And this is an integral curve of the differential equation y prime equals minus x over y. So if you think of the circle, there are only two functions whose graphs are on that circle. The function which corresponds to the top half of the circle, y1 equals square root of a squared minus x squared, and the bottom half, y2 equals minus the square root of a squared minus x squared. And you can check if you take each of these. First, you should graph these to make sure you understand what's happening. And you should check that when you differentiate this and plug it into this equation, you get a solution of the differential equation. Similarly, here we have a more complicated function and a more complicated differential equation. And we're told, and you have to verify this, that this is in fact the solution of this equation. Well, how do you do that? Here's the function x squared over 3 plus 1 over x. If you differentiate it, you get 2x over 3 minus 1 over x squared. That's y prime. So plug that into the equation. xy prime is x times this plus y, that is plus this. And if you multiply through and simplify, you see, in fact, you do get x squared. So this is the solution of the differential equation. It's a solution wherever this is defined, of course. It's not defined when x is 0. So you can take any interval which is on the positive axis or any interval on the negative axis, and this will be a solution on that open interval. It's not a solution on any interval that contains 0 because this is not defined at x equals 0. And there are more examples of differential equations. Now, in all the examples, in many of the examples we looked at, we found a one parameter family of solutions. So here was like the very simple case. Solve the differential equation y prime equals x cubed. So the solution is x to the 4th over 4 plus any constant. But then you can impose what's called an initial condition. You want to find not the general solution, but the particular solution where the function y evaluated at 1 is equal to 2. So you want to find the constant c such that y of 1 is equal to 2. So you want 2 to be equal to y of 1. If you plug in x equal 1, you get a 4th plus c. Solve for c, c is equal to 7th fourth. So this is the solution of what is called the initial value problem. And there are more examples. Now, there's one other thing I want to point out in this chapter, because it gives a very good, what you might say, geometrical understanding of a differential equation. Here's the first order differential equation. Y prime equals f of x, y. So you have some function that you want to find, and you're told that dy dx at any point xy is equal to this. Well, what is dy dx? Dy dx, you learn immediately in first semester calculus, is the slope of the tangent to the curve y at the point xy. So if you think of a curve that's a solution of this differential equation, at the point xy, the slope of that curve, dy dx, is f of xy. So you could imagine drawing a picture. Here I take some rectangular grid, and at each point in this grid, at each xy, I calculate y prime. So here's an example. It's a more complicated example, but every example with integral curves is kind of complicated. Here's some differential equation. Right, there are three different differential equations. I'm just looking at the first one. So we like to find a function y whose derivative satisfies this equation. But this also says that the slope of the curve, the slope of the tangent to the curve at the point xy is equal to this. So at every point in the plane xy, you can draw a little arrow whose slope, whose direction is this. And so you get this collection of arrows in the plane. These are the slopes. At each point, it's the slope of a solution that goes through that point. So each little arrow is like it's pointing in the direction to the tangent to the curve at that point. And this is what is called a direction field. A direction field assigns to every point a vector in the direction of the solution to the differential equation. You cannot do this by hand, except in simple cases. A little bit later in the term, I will tell you how to download Maple for free from the CUNY email. And you can use the program Maple, the computer algebra program, to solve differential equations and draw direction fields. So it is extremely useful today that we have the technology to do that. There's several computer programs that will do that. One is Maple, and that's the one we use at CUNY mostly. But these are direction fields. So it doesn't tell you what the solution of your differential equation is, but it tells you at every point what direction a solution curve is going through. And if you look at these arrows, you can actually sketch what solutions look like. So you can draw solution curves to your differential equations just from the direction field. Like here, you look at these arrows, your curve is it has to go like in the direction of these arrows. It's going along like this. There are lots of different solution curves. Because in general, there's a one parameter family of them. Okay, well, lo and behold, that really is all of chapter 1. It's very much an introductory chapter. And in the next lecture, we will start with chapter 2 and start to learn how to actually solve some differential equations. This will be on Zoom. This will be on YouTube. And you know from the website, from Blackboard, how to find our ordinary differential equation lectures on YouTube. That's it.